All right, kiddos, here's our last thing. Um, on your note sheet, if you've printed it out, this should be on the back. There are 3 graphs, one of EMF as a function of time, one as current as a function of time, and one as of power as a function of time. Now, one of the things that you'll notice, oftentimes when we're talking about a value that varies as a function of time, right, we can say that there's a maximum value, but sometimes it's helpful to also have an average value. But if we look at EMF and we look at current, since the current and EMF are oscillating about 0, the average current and the average EMF are 0, and that's not super helpful. And so in those situations, what we're looking for, a tool that we've come up with to kind of get a sense of the average, is called RMS. Okay, RMS stands for root mean squared. So to find RMS, you square all the values, and then you take the mean, right, or average, and then you take the root, so square root. Okay, so this is called root mean squared, but to find the root mean squared, you need to do those things backwards. Square the values, right? By squaring all of like your EMF values, you're making them all positive, right? And that's the problem, having the same amount of positive EMF as negative, so the average is 0. If you square them all, right, all of the values become positive. Then you take the average of the squares, and then you square root them all, and that gives you the RMS. And that's kind of gives us an average style calculation. All right, so let's do that. First, we need to come up with a function for the EMF as a function of time and for current as a function of time. We know that they're sine waves. And as an aside here, please remember that period is, if you remember from your math class or from patterns physics, period is the time for one rotation or oscillation. I'll abbreviate it there because I'm running out of space. Okay, so time gives us, it's capital T because it's a specific time. Capital T is a time specifically for one rotation or oscillation. Okay, and then there's frequency, which is how often something happens, and that's 1 over time. So period is time per rotation. Frequency is rotations per second, essentially. Okay, and then there's angular displacement and angular speed. Okay, so when you've got something that's rotating, typically we don't talk about linear frequency and things along those lines. We talk about angular speed and angular displacement. Okay, so angular speed is abbreviated. It looks like a W, but it's the Greek letter omega. It's lowercase omega. Okay, and speed is distance over time, right? And if we have that coil rotating, right, in a circle, the distance that it travels is 2 pi radians, right? 2 pi radians in a time of 1 period. We could also write that as 2 pi times the frequency. Okay, so the angular speed is in radians per second. Okay, and then the angular displacement is literally like what angle, how far angularly has the coil rotated, and it's equal to angular displacement. You know, like regular displacement is speed times time. Angular displacement is angular speed times time. Okay, so those are our asides because we need to write an equation for EMF as a function of time, and that's just a reminder. You guys in your math class, I'm sure, have written equations for oscillating functions for sine and cosine. So here, at any one time, the EMF at any one time is equal to the maximum EMF, right? E naught. And this is a sine function. And in the argument is omega t, right? Because it's the sine of the angle, and the angle is a function of the angular speed. Okay, and what we're interested in is what the EMF would be at any time, right? So time has to be in the argument for that sine function as well. Okay, so let's apply to this an EMF at any point in time. We need to apply our root mean squared, right? So if we square, we get E squared equals E naught squared sine squared omega t. Okay, and then we've got a handy dandy little trig identity that I know you love trig identities. So sine squared omega t is equal to 1 minus cosine 2 omega t over 2. Okay, so we stick that in for sine squared. Okay, so we are going to stick that in, and we get E squared equals E naught squared over 2 times 1 minus cosine 2 omega t. Okay, it's running out of space. Now you see that I moved this over 2 here to underneath the E naught squared just for funsies. And then if you take the average of a cosine, okay, so here we squared, we did a replacement, and now we're going to take the average or the mean. If we take the average of cosine, that becomes 0. All right, and so what we're ending up with is after the mean, we've got E squared equals E naught squared over 2, right? That's all we've got left. And then finally, we're going to take the root. I'm running out of space here. Root. Okay, so we're taking the square root of E, taking the square root of E naught squared, and we get E naught. And then they take the square root of the 2 in the denominator, get square root of 2. And if you look in your data booklet under topic 11, you'll see this equation. Here, let me write this bigger. Okay, so E, what we found is the RMS. ERMS, the RMS value of an EMF is equal to the maximum EMF divided by the square root of 2. All right, for current, similarly, right, going through the same process, the current RMS is equal to the maximum current over the square root of 2. Fun fact, you don't have to do that derivation that I did ever again. I just wanted to show you how we got there instead of just throwing equations at you. All right, now what about power? Because power, right, you could take the average, right? Because power is positive. For power, we've got, if we're talking about current, voltage, anything like that, so you could do power equals I squared R, right? To get any power value, because I squared is positive. Right, you could find maximum power by multiplying maximum voltage times maximum current, right? And in power transmission and AC, voltage, V, and EMF, E, are going to be used interchangeably. And they just are. And they're the same thing. Okay, because they're both measured in volts. All right, but they're just going to, you'll see different notation all over the place, and they mean the same thing. Okay, so you could do maximum power equals maximum current times maximum EMF or voltage. And then you could do average power. Average power. You could also write this as PAVG is equal to 1/2 of that maximum voltage times maximum current. All right. And you can also do current RMS times voltage RMS, right, to get the average power. Okay, and then finally, using Ohm's law to get resistance in that circuit, you could use maximum voltage over maximum current, right? And the ratios should be the same for the RMS values of the voltage and the current. Okay, so please take a look in your data booklet at topic 11. Okay, and make notation in your data booklet about what each of the terms that we talked about today mean and how you should use them. All right, and then in Canvas today, I posted a little bit of homework. So take a look at pages 439 through 444 in your Oxford textbook. That'll be your reference, in addition to the notes today for answering questions 1 through 4, right on page 471, and that's in the back of topic 11. All right, let me know if you guys have questions. Have a great day.